5, add edges and vertices to the second graph that will make the two graphs isomorphic. Okay, I think isomorphic graphs is kind of a hard thing to understand, all right? So one thing that helps, I think, is to put labels in there. So let's say this is A, B, C, D, E, F, G, H. Okay. I see 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices, and the other one only has 5. They're not isomorphic. That's why they want me to add edges and vertices. Okay. But in order to do this, you need to pay real close attention to the relationships. One way to look at that is the degrees. This one right here is a degree 2, and it's connected to a 3 and another 3. So I might, in this graph over here, look for a degree 2 that's connected to a couple of degree 3s. So I might label this as E prime. That's my degree 2, and maybe this is A prime and this is F prime. I've got a degree 2 connected to a couple of degree 3s. So then that triangle, just imagine if I moved this magnet around, it would look like that. Okay. So look at A. See how A is connected to B over here? This thing, that point right there, I'm going to call that B prime. And then if you notice, you've got C and D sticking off that B. So I can just add that on there. Okay. Now look down at F. F goes to G, so that means this point right here must be G prime, and then we need to add on one more to get to H prime, and it doesn't have to be a straight line, but that's what we're looking at. We should have the same number of vertices, the same number of edges. All of the degrees are the same. All of the relationships are the same. That's what's going to make these isomorphic. Number 6, determine the number of edges and the sum of the degrees of the vertices. So number of edges, 1, 2, 3, 4, 5, 6, 7. I see 7 edges. Now look at the degrees. You've got a 2 and a 4 and a 3, a 2 and a 3. So the sum of degrees, 4 and 3 is 7, it's 9, 12, 14. 14. The sum of the degrees of all of the vertices is 14. So do the same thing over here. I've got 1, 2, 3, 4, 5, 6. 6 edges. And my degrees, I've got a 2 and a 3 and a 4 and a 3. That's what? 12. Sum of the degrees is 12. And you're supposed to notice a pattern, okay? See how the sum is twice as much as the number of edges? That's this next thing right here. That's the sum of the degrees theorem. Put a star by that. That's going to come back at some point. The sum of the degrees theorem. In any graph, the sum of the degrees of the vertices equals twice the number of edges, okay? The sum of the degrees of the vertices equals twice the number of edges. Number 7, a graph has precisely 6 vertices, each of degree 3. How many edges does this graph have? Well, if you've got 6 vertices and each one has a degree 3, then that must mean the sum of the degrees is 18. The sum of the degrees is 18. So then how many edges would there be? Right. Must be 9 edges. Number 7, draw a graph representing the relation. There's a direct bus link. What's the significance of the graph being connected? So really this looks like the same thing as the seating assignments at the beginning of the lesson. we're going to draw a picture of all of this stuff and look at their relationships. So again, I'm just kind of going to put some dots in a big circle. Doesn't really matter. Grand Forks and Fargo, Bemidji, St. Cloud, Duluth, Minneapolis, Escanaba, Green Bay. Okay, so I've got all these cities, all these dots, and I'm going to work on their connections now. Grand Forks has a bus link with Bemidji and Fargo. Fargo goes to Grand Forks, which I've already got it, St. Cloud, and Minneapolis. Bemidji goes to Grand Forks, got it, and St. Cloud. St. Cloud goes to Bemidji, got it, and Fargo, got it, and Minneapolis. Duluth goes to Escanaba and Minneapolis. Minneapolis goes to Fargo, which I've got, and St. Cloud, which I've got, and Duluth and Green Bay. Escanaba goes to Duluth and Green Bay. Green Bay goes to Escanaba and Minneapolis, which I've got. All right, so do I have them all? Did I miss anything? So what we've just shown is all these connections, specifically these bus routes, the direct link. And we're going to use this graph later to solve a problem like, what's the best way to get there? What's the fastest way to get from city to city? Okay. What is the significance of this graph being connected? Well, if it wasn't connected, we wouldn't be able to get from all of the cities to all of the other cities. So the fact that it's connected allows me to get from city to city, from any city to any city. Being connected allows us to get from any city to any city.